Hello everyone. So today we'll be discussing various machine learning algorithms, supervised machine learning algorithms. So without any further ado, let's begin with it. The first algorithm that we have, and the easiest and the most widely used, I would say, is linear regression. What a linear regression does is that it takes a bunch of continuous variables and then it predicts the continuous in the form of continuous variables itself. Now, how do we do a linear regression? How does it work? As in, like, how do we understand how it works? So basically, what happens is that we are trying to find a best fit line. So the best fit line is our predicted variable. So it's our predicted output. Now what it tries to do is that from the actual output, how close this best fit line should be. Now, how do you understand how close this best fit line is? So the best fit line should be in such a manner such that the error or the residual between these the difference between the actual and the predicted value is like the minimum. So that's our main agenda of linear regression. So what we are trying to do is we are trying to find a best fit line which reduces the error between the predicted and the actual values. Now, there are certain assumptions which we need to follow while we're doing linear regression. First being that there cannot be any multicollinearity between the independent variables. Secondly, the errors must be normally distributed. Third is that it should be homoscedastic. And fourth is that there should be a linear relationship between the dependent and the independent variable. The second algorithm that I would like to talk about is logistic regression. Now, what logistic regression does is that it takes a bunch of continuous variables, right, and it classifies them into binary classes or multiple classes depending on how many classes you want. So what it does is that it will take a bunch of continuous variables and then turn it into dichotomous predictions, right? So what happens, how this works is that we give the algorithm a bunch of continuous variables, as in like independent variables are continuous. So what our algorithm does is that firstly, depending on the value of z as in, let us take z is the prediction that we are making, right? So according to the value of z, according to the prediction that we are making, this turns it into a sigmoid function. So what happens is that now sigmoid function is a function which takes values from 0 to 1. So what happens is that when z is less than 0 or very less, right, the value of z is very less, this sigmoid function, it turns this thing to almost close to 0. And if z is a lot higher, so it becomes closer to 1. So where is our decision boundaries? That the decision boundary is at 0.5. So it will be either less than 0.5 or more than 0.5. Now whatever is like so next up what we do is that whatever is less than 0.5, we can term that as class 0, and then whatever is greater than 0.5, we can term that as class 1, depending on the probabilities. Now, a very important concept in logistic is the loss function, right? So like linear regression, it also has the loss function, looks pretty similar to the linear regression. The only difference is that in logistic, the loss function takes value of 1 by 1 plus e to the power minus x. So what happens is that this loss function, so depending on how close the hypothesis that we're making, so how close the predicted value is to the class, the penalty is given. So if we are predicting that there is a 0.3 probability of class 1, but class 1 actually happens, so there will be like this major penalty which will be inflicted upon it. So that's how basically the loss function looks pretty similar to the gradient descent loss function in linear regression, but this is called the maximum likelihood, because we cannot directly use the linear regression loss function, because what happens is that then our algorithm, the predictions, there will be, we are trying to, our loss needs to be the minimum, right? So what happens is that there will be a lot of local minimum if you're just trying, if you're following the simple gradient descent path and not the maximum log likelihood path. So just to get a convex gradient descent, we are taking the maximum log likelihood and not the simple gradient descent basically. So now I would like to talk about decision trees, one of the most widely used for supervised and unsupervised learning. Now what we've noticed in linear and logistic regression is that it either can be used for a regression problem or for a classification problem. Decision tree is such a thing which can be used for both regression and classification, but it is most widely used for classification problems. It fits outliers much better than a linear regression. It's a good classifier, much better performance than logistic regression is what I would say. So the two major decision trees, types of decision. So okay, before we go into the types of decision trees, let us first understand how a decision tree works. So what happens is that we have a group of people. Suppose we have boys and girls who play cricket. Now we want to separate them into two classes. So how will we do that? So there's multiple ways how we can separate them. We can either separate them by gender, or we can separate them by their age or their height or whatever it is. So we can separate these two classes into two. Now how do we choose how to take the first decision? What is the most important decision that we need to take? So that will depend on the probability. The one which has when we are dividing these two, whichever has the highest probability or the highest information gain, if we are dividing in these two into different classes, so which is the most homogeneous, right? So that is our main agenda, as in which is giving the most information about a class. So that is how basically the split is done. So there's different ways to do this split. The first way is Gini. Now Gini, the more the value, the better, and Gini can only be used when there is a yes and no question only, right? So it can only work in a success failure like this. That's the only option for Gini. And the higher the value of Gini, the more homogeneous or the more information gain we say. The next is entropy. Now the lesser the value of entropy, the better split it is. So the more information gain there is. So there are three types of actually decision trees ensemble. So the first is bagging. In bagging, what we do is that we take our data set. Now we sample the data set into multiple various small other data sets, and we perform a classifier on each of them. Now what we do is that we can either take the 4 out of 6, whatever is the average value, just as in for regression we can take the average value that we're getting out of these classifiers, or as in for classification problem we can take the class which is being identified the most number of times. So one very famous way of doing this is the random forest. So in random forest we make multiple trees out of that one data set, and this will predict what is which class has more probability of happening. So what most of the trees, what is the class that they are predicting, so it will be taking that, right? The next method is boosting. So in boosting, what we do is that we have a weak learner, and this weak learner will be learning itself. So it's a sequential process. So what happens is that as the algorithm goes on, the learner learns itself. So every time there is a iteration, the learner will learn something new, and then another something new, and then another something new. So a very popular way of doing this is called the gradient boosting method. Now in the gradient boosting method, what happens is that we are taking the loss function, or we are taking the error as the learner. So in our first iteration, the error will be suppose very high, because it's a weak learner, right? So the error will be very high. So what will happen is that now the error is very high in the first tree. So this error will go now to the second tree, and it will, as we are increasing, so as we move forward, right, so the error gets lower and lower, so our algorithm learns better and better. Now in gradient boosting method, there's a better way, which is called XGBoost or extreme gradient boosting. Now it was built on gradient boosting, but it is much better than gradient boosting, as in it's very good at handling outliers, doesn't get affected by that. It can handle missing values very well, so it has a much better performance. And a lot of decision tree work is, especially random forest, is kind of like, it is a little bit of black box. We don't know exactly what is happening in a random forest. So yeah. So what we found out, like the main thing that we have found out from this, is that bagging, there's a parallel process happening, right? And in boosting, it's a sequential process. But in XGBoost, you will notice that it can move parallelly too. So if there's like a big data, XGBoost can handle very easily, as a random forest will be quite slow in that. So we can use XGBoost if there's a huge amount of data to, like, it can run parallelly. It is actually that powerful. So the next method that I would like to discuss is called KNN. Now KNN is it's called a lazy algorithm because it doesn't really follow any mathematical or any algorithmic way to solve anything. All it does, it's very simple, right? All it does is that we want to predict value. So what we can do by KNN is that, so we have a value, and we want to predict the closest values to that. So we can take a KNN. So the more the number of the neighbors, and the more the number of assumptions, like number of neighbors that we're increasing, so the better the assumption on that prediction is. So we want to predict something, and we have various neighbors. So the number of neighbors that we're increasing, so a more how do I say this, concrete assumption that we are making. So KNN, what it basically does is that it uses Euclidean distance. So there is no proper algorithmic method for KNN. It just uses, all it does is just uses Euclidean distance, right? So what we're trying to do is that, like, if we are increasing the number of neighbors, so the line, or the best fit line, or the assumption actually gets better and better, and we can actually, like, optimize this, as in how many number of neighbors that we need, right? So that can be done. So that's basically about KNN. So the final one for now that I would like to discuss is called your SVM. Now support vectors is just like, it's a very intuitive method of doing it. It's very similar to logistic, but there's a small tweak in it. So in support vectors, see, our logistic has a very linear decision boundary, right? So it has only a line which can divide two classes. What do we do if those two classes are not easily separable? That's when our support vector comes into picture, like it's one of the best ways to do that. So firstly, let's just get into it, right into it. It has a margin, right? So there is a class, there's one class on one side, and then there's the other class on the other side of this margin. So the margin that we increase, the higher the margin distance that we have, so the more tightly they are separated. Now how do we make this margin? We make this margin by, first line is taken on the support vector of one side. So the support vector on one side is the data point which lies closest to the other class, so that is the support vector, and in the next class we do in the same way. So we take the distance between them, and that is called the marginal distance. Now we have to increase, the more that we increase the marginal distance, the more the accuracy increases. But there is like a problem in that, as in like the data might just overfit, so like we cannot just keep increasing the margin of distance, so it needs to be an optimal value. Now this is that distance that I'm talking about, and the line which is separating them, that is in 2D, right? So what do we do if it is in 3D? There are ways to do that too. So how do we do that? We take this method called kernel. Okay, so we have this thing called kernel. Now changing the kernel, we can actually go from 3D to 4D and so on. Now if you're taking in 3D, it is no more a line, so there is a plane which is separating these two variables. So one part of the variable will be on, suppose, top, and then one class will be suppose on top and the other class will be down, and there will be like this plane which is like separating them. So in the same way we can take in 4D, 5D, and as many as we want by the simple kernel method. Now also we can increase the distance between them or decrease the distance between them, the margin distance, by its C value. So our C value needs to be optimal, right? And it shouldn't be too much or it shouldn't be too less. Now the loss function of your SVM is actually pretty similar, except that remember in logistic I told like the loss function takes the sigmoid function as in 1 plus e to the power minus x, right? But in SVM what happens is that it takes 1 by 1 plus e to the power of minus x square. So yeah, so it does descend by gradient descent by that. Now what happens is that like when we're taking e to the power of minus x square, there is a bigger penalty. So if a data point tries to escape its class, and if we are making a wrong hypothesis, there's a much bigger penalty than there is in logistic regression. So the accuracy actually is much higher, because it's a strict boundary, it's a very strict boundary, and it's much better because it's not a linear decision boundary. It can work on any planes basically, and it's an optimal way of, much better way of doing the logistic regression. So